Hello, are we online? Yes, okay, perfect. All right, so welcome everybody to this workshop that we are hosting today at University Carlos III of Madrid, in which we want to show the advances regarding to automated driving that the Renault Group is developing in the latest years. This workshop's been organized by IEEE, the Spain section. I have here the president of the Spanish section, Edgardo Castronovo. Welcome.
Thank you.
And also by the Spanish chapter of the Intelligent Transportation System Society of IEEE. I'm here the representative of one of the members of the EXCOM of the society. My name is Fernando Garcia. So before welcoming to the speakers today, we're going to have three speakers from Renault explaining the different technologies that right now we have in autonomous driving. We want to give you one hint of what IEEE is, mostly IEEE Spain and the Intelligent Transportation System Society are. So I'm going to just ask you just 10 minutes of attention so we can introduce you this society, and then we're going to move to the presentation that Renault is going to provide to us today. So we're going to start with IEEE Spain. So Edgardo, please, if you want to talk to us about IEEE Spain, please go ahead.
Thank you, Fernando, and thank you, the chapter, for this invitation. Well, I want to show briefly the IEEE Spain section. Maybe we can start talking a little about what is IEEE. The main objective of IEEE is to foster technological innovation and excellence for the benefit of the humanity. IEEE is conformed all by volunteers. We are not paid for working in IEEE. In fact, we have to pay to be member of IEEE. And nowadays, the largest scientific and technical organization in the world. It started at the union of two organizations from electrical and electronic engineers, but nowadays it's a large family with physicists, mathematicians, computer scientists, lawyers, economists, a large family around these areas of electrical, electronic, and neighbor areas. Right. Nowadays, we are almost 500,000 persons, of members in all the country. We have 38 technical societies. The technical societies are the group of members that are joined following a branch of knowledge. We are established in 160 countries. We sponsor or organize a lot of conferences by year, documents, and we have a lot of journals related with these areas. For one geographical organization, we are divided in 10 regions. We belong to the Region 8. The Region 8 is the largest geographically, and the second one in number of members. As you can see here, the largest region is the Region 10 in number of members, but we are the second one. And it's true that this is the region with the greatest diversity. That is the last wars that we have experienced in our region affects greatly the activity. That is, we have members, of course, in Russia, we have members in Ukraine, we have members in Palestine, and we have members also in Israel, and not to mention Africa. And therefore, it's not quite easy to work together wanting to promote the technology for the benefit of the humanity. Not so easy. Right. Looking at our section, that is the Spain section, we have now more than 55 years. We are around 3,500 members spread across the country. From the 38 scientific societies, we have a representation here of 30. That is, we are only lack of 8. scientific societies. We have 3 affinity groups: young professional, life members, women and engineering, and 22 studying branches. I am the chair nowadays. The next chairs, I am the chair for 24 and 25, and in 26 and 27 it will be Antonio Robles. The election was performed a month ago, I think. And we are between 25 and 30 volunteers from all over the country. You can see here what are the areas that we are working on nowadays, and the people that that are responsible for these areas in the section. And you can see here we have members from Sevilla, La Rioja, Extremadura, Valladolid, Vigo, Catalunya, from all around the country. Therefore, you can see that most of our activities is performed virtually. We have 2 meetings in person by year, but in general we work virtually. What are the activities that we are performing? Right. We are the representation of this large organization in Spain. We are the representation facing the national and local governments. We represent also the IEEE members of Spain in the region. I have to go in this weekend to one meeting of the region. And also at the global state of IEEE, we represent the Spanish members. We want to coordinate the chapters, that is, we want to make that the activities of the chapters are unified, are coordinated. We don't want to make parallel activities in the same file, and therefore we want to establish synergies between them. We have the treasury of most of them, the small ones. We give support to the chapters, maybe mainly in these smallest chapters. It's difficult to renew the authorities, and therefore we give support to them. And also we work a lot in the transversal activities, that is in the activities that are common to all the chapters. That is working with the branches of students, the young professional, the people that are going out from the university and going to the real work, and also, of course, to improve the participation of women in engineering. As you can see here, 80% of our members are men, and only 13% are women, and this is a very dramatic number, and therefore we are going to improve the participation of the women in the STEM activities. We have looked at one of the problems in the section is the dissemination of the information. That is, we know the activities performed by our chapter, but we don't know the activities in other chapters. And maybe we have to send a PhD student, or we are going to send a paper to a conference, and we have a conference here in Spain, and we don't know. And therefore, we are sending every 2 weeks an email newsletter with conference, visit, free tickets for ferries, and so on. We have agreement with companies, as Renault here. With other brother association, has the Institute of Engineering of Spain, the Young Academy of Spain. We have also agreement with universities, has the University of La Rioja and Internet, and also with some technological shows that we consider that are important. And also, we want to improve the membership of our members. In 2 weeks, we will have a meeting, a virtual meeting, for those members that want to be senior members, and therefore to help them to prepare the curriculum vitae, to obtain the reference, therefore be aware of that. We are sponsoring between 15 and 20 conferences in the country by year, and therefore we have to perform the quality control of this conference for using the logo of IEEE section, right? We are promoting the action in standards and technological activities and standards of IEEE. Nowadays, there are more than 80 standards of IEEE in preparation, and therefore we want that the Spanish members work on the preparation of the future standards of the industry. And of course, we give awards, recognitions, we organize visits, and so on. Well, we invite you to participate in the section, to collaborate in the section. Only you have to write to this email address or to visit our page and go through it. Thank you, Fernando.
Thank you very much. Thank you so much for the presentation. It was very nice. I really recommend everybody to go to the webpage of IEEE Spain section because it's a very active community. Before we move for the presentation, I want also to give you a very, very short hint about what IETSS is, because IETSS is one of the societies that Edgardo was mentioning, that is the society working in the intelligent transportation system. And here this workshop is co-organized by the Spanish chapter of the society, which is the members of the society that we are actually working in Spain. We have some people. We're last count it was around 100 more or less people from the society actively working in Spain. I'm going to go very fast because I just want to give you what we do, just from the general perspective, because I think that everybody is really expecting here for the first speaker. But just for you to know, Intelligent Transportation System Society is a society from IEEE that is focused in the development of the transportation system and the IT technology within this field. It is close from general communication technology to artificial intelligence, which is one of the main topics, for example, today. This society has different branches, different pillars of the society. Those six that you have here, we work in a standard, we have technical committees, we have educational activities, we have awards that we give to those people who bright within the society. And then we have the two main activities that we have is the conferences and the publication. So the two main conferences that we have is Intelligent Vehicle Conference, Intelligent Vehicle Symposium, that's it's going to be hosted this year in Korea. And the second conference is Intelligent Transportation System Conference, ITSC, which next year is going to be hosted this year it's going to be hosted in Canada, but last September was hosted here in Spain in Bilbao. We also have other conferences like CBS, AEC, but these are the more conferences that you may have more information in our webpage. And the other important thing that I also want to share with you is that our publications. We have 4 main journals: Transaction ITS, Transaction Intelligence Vehicles, Open Journal on Intelligent Transportation System, and Intelligent Transportation System Magazine. Those are top journals in the field. They are in the top of the rankings. So I recommend you also, if you are interested in publishing something in the field of transportation, to go and check them out. This is everything I wanted to explain to you. I really want to move forward for the first presentation of the day. So I'm going to ask Carlos Guindel, Dr. Carlos Guindel, to come to the stage and give the first introduction. Carlos, everything is here. And also, I want to give you first, before he starts the presentation, to a small introduction to Carlos, because Carlos he was former PhD student of this university, of University Carlos III of Madrid. And I had the luck to work with him for around 10 years, I think. So it's really nice to see him right now developing in the industry. He's going to talk to us about the sensing and perception in the intelligent vehicle architecture and the work that he's developing in Renault. Carlos joined Renault last December, no, Carlos, or November 2023. So I'm sure he's gonna be able to give you a really brief update of all the state of the art of technology that Renault is developing. So Carlos, if you are ready.
Hello?
Yes, you're ready. We can hear you. So,
Okay,
the stage is yours.
We need our presentation, but okay. So, thank you for the presentations, and thank you to the IEEE for this opportunity to present here. As Fernando said, we are members of RTS, which is Renault Technology Spain. Okay, and the idea today is that we are going to review the technologies that can be used to make vehicles more intelligent. Okay, so this is the plan for the presentation today. Okay, and I will be presenting the introduction and the sensing and perception part, and then we will have Eduardo presenting the maps, localization, and navigation part. And finally, Francisco will finish with the control and supervision and the conclusions. Okay. So I want to be fast because I want to be late, so I will start with the introduction. So, okay, it's okay if some of you like driving a lot. I like it too, but the truth is that human beings are not very, very good at driving, okay? Because, yeah, for example, most of the accidents are due to human factors. So it seems like it could make sense to use technology to help us in this task, okay? So probably some of you already know the information that is in this slide, okay? Because it's the levels that were defined for the increasing automation of the tasks of a vehicle. Okay, so they start at level 0, which will be the very old cars without any automation. Then we have the level 1, which is feet off, in which the car can control the pedals. Then level 2, hands off. There are systems to control the steering wheel. And then there is a big gap until level 3, which will be eyes off. That is, the driver can forget about using the eyes to see what is happening around the vehicle. Okay, then we will have level 4 and level 5 until the complete automation. Okay, so these 3 first levels are the ADAS, the Advanced Driver Assistance Systems, that we have now in the market. Okay, and that those levels will be autonomous driving. Okay, and today regulation is ready for this. Okay, and it's what any new car has, but for those levels, the legal regulation is still under development. So, yeah, it's what we can expect for the future. But this is also what makes current cars intelligent. Because, for example, from this summer, every new car that is sold in Europe needs to include these systems. Okay. So, for example, they need to be equipped with advanced emergency braking, with lane keeping assistance system, okay, with drowsiness and distraction monitoring, okay, and all these systems, as I said before, are intended to help the driver, okay, and let's say make the car more intelligent to help the driver in his tasks, her tasks, okay, and for all these systems, okay, we need to do a lot of things under the hood, okay, and this is what a typical intelligent vehicle architecture looks like, okay. So we have at the beginning an acquisition block, which is made of sensors that are gathering information about the environment, okay. Then we have a perception block, which is responsible for understanding this data that is captured by the sensors. Then we also have a communication block, okay? And all this information goes to the decision block here, okay? This decision block decides what to do, then send it to the control block, and this control block decides how to do it, and sends this information to the actuation block, which is the one operating on the wheel, on the throttle, on the brake, and so on. Okay? So today we're giving a brief overview of some of these blocks, okay? And this is the idea for today. And I will start now with the first two, which are the sensing or acquisition and perception blocks. Okay. And, well, this part is essential for any intelligent vehicle because for a vehicle to be intelligent, it has to be able to make decisions based on the environment. So it's important to have a view of what is happening. Okay? And basically, this module, what does is to receive raw sensor data and delivers a model about the world that is surrounding the vehicle. Okay? And this is essential for obstacle avoidance and for following the traffic rules and basically for everything. Okay? And in the end, the quality of the decisions that we can make is as good as the quality of the world model that we are building with this block. Okay? Because if we are making decisions based on bad data, then the decisions will be also bad, of course. So this is a really, really intelligent car. Okay? It's a prototype by Waymo. Okay? They're trying to get to level 5 of automation. Okay? And when we look at this car, okay, we realize that it has a lot of weird stuff here and here and here. Okay? And of course, all of these are sensors. Okay? Sensors are getting data about the surroundings of the car. So for example, here we have a LiDAR and also a lot of cameras. Here, this is cameras and radars. Okay, so basically, when we want to increase the automation of a vehicle, we need to use sensors. Okay, and this perception part will be essential in this. Okay, but apart from these fancy sensors in a vehicle, we also have some what we call the proprioceptive sensors. Okay, that are responsible for getting information about the internal state of the car, okay? And this is also important because we need to measure the ergodynamics and also the displacements of the car. This is like the first step, okay? And then once we have this, we can go to the next step, which is the exteroceptive sensors, which has cameras, radar, and so on. Basically, every sensor that is looking outside, okay, as we can see here. Okay, this is the typical distribution of these sensors and what they see in an intelligent vehicle. Okay? So for example, we have a radar for long distances, we have ultrasounds for very close distances, and so on. Okay? And in these exteroceptive sensors, we also have the GNSS, okay, which is important, but it's a particular case because it's giving information about the state of the vehicle. Okay, so this information that we had here. Okay, and regarding these exteroceptive sensors, okay, the most usual ones are these that you can see here in this slide. So we have cameras, which are important because they are similar to human eyes, okay, and roads are made for human eyes. So of course, this is very important. And we also have 3 types of active sensors, which are LiDAR, radar, and ultrasounds. Okay? And they are active because they need to send waves and then get information from the reflect, as you can see here, basically. Okay, and these are very good at measuring distances, okay, but they don't give the same information as cameras, as we will see in the next slide, okay? For those of you that don't know this, this is basically what the LiDAR information looks like, okay? There are a lot of points in 3D, and yeah, representing the distances to the objects in the environment, okay? And the radar is something similar, but it's much more sparse, okay? So it's like these red points here. Okay, so as I said before, cameras are good because they have high resolution. They provide appearance information, which is really, really useful. But they don't work very well in poor visibility conditions. So for example, in fog or rain. Okay? And also they have high computational requirements. And if we are using monocular cameras, we don't have depth information straightforward. Okay? For the radar is okay for all kind of weather, but also it's good at estimating velocities, okay, because of the Doppler effect, and the range of detection is very long. but resolution is very low, the field of view is also very low, and it produces a lot of noise because it's not easy to interpret the information given by this sensor. So in general, we have a lot of noise. Regarding the LiDAR, it's able to provide accurate depth information. Also, it works well in different lighting conditions, but it's also affected by other weather conditions, so fog, snow, and so on. And it's expensive, okay? And finally, ultrasounds are only useful for very, very short range, okay? So it's basically for parking assistance and so on, okay? Because the range and the resolution is not very high. So, as we have these types of sensors, okay, and we have the cameras that give a lot of information, but it's not really useful to get this depth information, to get 3D information, and we have radars and LiDARs that are able to give rich 3D information, but are not so good distinguishing objects, okay, because we don't have the appearance, so only the points. It seems like a good idea could be using what we call sensor fusion, which is trying to merge information from 2 or more different modalities, 2 types of technologies. And thanks to this, we can get more accuracy, more consistency, operation in all weather, and noise reduction. And this fusion can take place at different levels. So for example, we can process the data from each sensor separately and then perform a fusion that will be high-level fusion. So this is easy, but it's not so useful because we are losing information in the procedure. Okay? We could stop at an intermediate point and then try to fuse this intermediate result, and that will be mid-level fusion. And finally, we could try to fuse the data from the sensors, the raw data from the sensors, or something that is very close to that, okay, and that will be low-level fusion. That is the one with the more quantity of information, but it's also hard. It's also hard because it requires taking into account all the data together, okay, and also it requires that the data is representing exactly the same scene. So for example, you require that sensors are triggered at the same time, and you also require that there is a very accurate calibration between these sensors. Okay, so for example, here we have some LiDARs, okay, these are points from the LiDARs, and we have the camera. If you want to perform this low-level or mid-level calibration, you need to be able to associate the LiDAR points with the image pixels in a very, very accurate way. Okay, so this is also important. Okay, so this is all in the sensing part. Then we have the perception part. Okay, and the perception part is responsible for understanding what the sensors are delivering. Okay, so we have the data, the image, the LiDAR cloud, whatever. We need to process it to get something that is useful for driving. Okay, so this is the role of perception. Okay, and here, of course, what is mostly used is machine learning techniques. Okay, and that you already know that they are able to learn from labeled examples, so you don't need to design manually the procedure. Okay, and especially deep learning networks. Okay, that's basically bigger machine learning models. Okay, and particularly an important architecture here are CNNs, okay, convolutional neural networks, that take an image, make it, try to compress the useful information into features, and then make decisions based on these features. Okay. Of course, now attention mechanisms are blooming, okay, so this is the new trend. But still, in all of this, we have some challenges. We need a lot of training data, the computational demands, and this is important because in onboard computers, we don't have a lot of power, a lot of capabilities. And also, it will be important to ensure reliability in all kinds of scenarios, okay? Because sometimes these networks, these models, behave as black boxes, okay? So they make decisions and we don't know why, and that will be a very, very important point for intelligent vehicles. Okay? So now I want to give you a very brief overview of some techniques and so on of perception. Okay, so one important technique or task that we can use here is semantic segmentation. Okay, that tries to map every pixel in an image or every point in a cloud to a semantic category. Okay, so for example, saying that this is a car, this is a person, and so on. Okay, that will be classic semantic segmentation, but then we have also what we call instance segmentation, in which we can distinguish between this car and this car. Okay, and this is obviously very useful. And we have the final step, which is panoptic segmentation, that tries to mix both things, because they are doing this instance segmentation for things such as cars or pedestrians, and semantic segmentation for stuff, such as the sky or buildings and so on. Okay, so if you do everything together, we call it panoptic segmentation. Okay. Usually here we use encoder-decoder approaches. Okay, so we have an image, we convert to the feature space, and then we try to go back to get an image like this. Okay. And well, this can be used, for example, for lane detection, which is a very important task in intelligent vehicles, as you can guess. Okay. So if you have a semantic segmentation, you can try to merge the points belonging to a line, and then try to identify the structure of the road. Okay, and this is a possibility. For this, we can also use anchor-based methods, because you know that the lines have a very clear structure. Okay, they're in the longitudinal direction, so we can propose some candidates and then try to fit them, okay, to make it closer to the real line. Or we can use also parameter-based methods, which tries to estimate directly the numbers that are in these line models. Okay, and usually they're less flexible. Okay? But here, this seems an easy task, but still it has challenges. You can find occlusions. You can have a car here, and then you won't see the line. Okay? You can have junctions, exits, because you have two lanes, but then you can have one, or you can have three, and yeah, you need to update your model. Also, of course, you can have cases in which road markings are deteriorated, and this is also a challenge for this kind of algorithms. Another critical task in perception is object detection, of course. We need to detect the rest of the cars and also the pedestrians. Okay? And here we have 2D object detection, which is like, a classical computer vision problem. Okay? So here the goal is to get 2D bounding boxes, okay, representing the objects. Here we have these boxes, but we also have an instance segmentation within the object, within the box, sorry. And well, here we're representing the position of the object within the image. Okay. Usually there are two main groups of algorithms. So there are one-stage and two-stage algorithms. Okay. These are faster, but these are a bit more accurate. Okay, and this is okay, but for driving, we would like to have what we call 3D object detection. That is the objects, but also where they are, okay, with respect to the vehicle. And, well, actually, we call it 3D, but actually, sometimes we can just simplify it to this bird's eye view, okay, because this is what really matters, okay, the relative positions in the plane with respect to the ego car. Okay. And for this, well, we can use just one modality, for example, cameras, and this is possible. But but I said before that the cameras are not very good at depth estimation, so the results here are less accurate. You could use LiDAR or radar, but then you don't have the appearance information, so probably you will have a lot of noise. And yeah, so it makes sense to go to fusion again, okay, and try to use different modalities together. Okay. So when we apply this fusion here, we can apply a low level or early fusion, again, as I said before. So you will merge the data before any processing, okay, or any significant processing. You can go with a high level or late fusion, in which you get the results for the camera and you get the results for the radar, for example, and then you try to merge them. Okay? Or you can apply a mid-level fusion, which is what we have, for example, here. Okay? So what do we have here? We have a 2D detection network, okay, providing detections in the image, and these detections are used as candidates for the LiDAR. Okay? We apply the LiDAR points on the image, so we obtain the 3D properties of the object, and we can estimate a 3D bounding box. Okay? And yeah, this is what we have here, for example. I think, yeah, probably I'm a bit late. So, but, well, here we are detecting the objects in the image, okay? And yeah, applying detection and instant segmentation networks. So we have the cars, the pedestrians, and so on, okay? And once we have this identified in the image, we can include the LiDAR information, okay? That it will be very, very useful to get geometrical information about the objects, okay? So we project the points onto the image, and we get the distances from our car, from the ego car, to the rest of objects, okay? So here's where the fusion is taking place, of course, in this case. And using this geometrical information, we can try to estimate 3D boxes, okay, as we will see in the next step. Okay, which is the final result that we are expecting, because this is the information that will be useful for navigation and, yeah, for intelligent vehicle to perform the functions. Okay. Finally, you usually have also a tracking stage, basically to make everything consistent, okay, and to ensure that the movement of the objects is, yeah, it makes sense. Okay. But I will go to the, to the next slide. Okay, and just to finish, these are some current and future directions. So, for example, one interesting line is to trying to take advantage of different information from different steps, okay, to get, for example, in this case, 3D boxes, okay. Also, labeling is still a problem, so the development of methods that reduce the data needed to train is also important. And for the future, I think that open set detection will be also important. As you can see, for example, in this image, when you train a network to detect cars and pedestrians, when you find a rock in the middle of the road, yeah, it won't be able to detect it. So it's important that the network is able to say, okay, I don't know what this is, but there is something there, okay? So be careful. And also, of course, as I said at the beginning, explaining the results of all these models will be also very important, okay, for the future. And I will finish here, so I will let Eduardo continue.
Our next presenter is Eduardo José Molinos. He got his PhD from Universidad of Alcalá de Henares and has been working in the field for a few years already. He was also working in Karlsruhe Institute of Technology for how many years, Eduardo? Like
for 6 years.
6 years. And he also moved to Renault in 2023, I think, no? So, Eduardo, the stage is yours.
Okay, I will start again. So, so Carlos has already presented how to understand the world that is around us, But now the vehicles need to do something with this world. So I will go to maps, localization, and navigation. That is the stages that work with the world around us. So first, let's talk about the maps. So we can divide maps between HD maps and SD maps, or navigation maps. And first, HD maps. So HD maps can be impressive, but we need to do these maps. So these maps can be done automatically from sensors, can be done manually, but are usually really, really expensive to do. We can include as many information as you want. So we can include road dimensions, we can include lines, we can include speed limits, we can include the appearance of the buildings, whatever you want. These are usually stored in some kind of database that can be accessed by the intelligent vehicle, but the problem is how we keep these maps up to date. We need to record again the maps, we need to redo the maps, so they are really, really expensive. And also about storage are really big. These kind of maps can be several gigabytes per kilometer. So we really need these maps for everything that the car is doing? No, that can be interesting for some tasks, but not for everything. So we can move to what we can call SD maps, so, or navigation maps. These maps has only the relevant features that we need for navigation. That usually is the lane geometry, the relationships between lanes, because we need to deal with intersections, with the roundabouts, with lane changes, and the traffic rules. So we need to know how fast we can drive. We need to know if we can change the lane or not in a specific position. What are the advantages? These maps are usually smaller, so we store only the relevant information for our task. We don't store everything that is around us. And as they are smaller, are also usually easier to keep up to date. So if we only need to store the geometry of the lanes, we can do that manually from aerial images. We don't need to go and record again. And of course, there is a lot of open source implementations of these kind of maps. So for example, I show you here the Lanelet 2 library that was a library developed inside the Karlsruhe Technical Institute. And if you want to work with this kind of maps, you can download the library, you can work with that. Then we move to localization. So localization is something that we have not only in every car, we have in every mobile phone at the moment. So there is several technologies for localization. Depending the accuracy that we need, depending what is our task, we need to go, let's say, deeper and usually more expensive, or not. So let's say level 0 cars, all cars. You have a mobile phone, you want to go somewhere. You are GPS only. It's available, it's cheap, but the accuracy is really low. So the accuracy, depending if you are inside a city, you can be several meters. You can be even 100 meters off. Is still enough for a person to localize. But is enough for an intelligent car to localize? Probably not. And it's also not available in some specific scenarios. For example, inside tunnels, you don't have GPS. You can go to the next sensor, it's RTK GPS. So this is a specific GPS that has also inertial units and has usually also base stations that increase the accuracy. It's better than before, but of course it's not available everywhere and it's more expensive. You need to pay for this service. It's not free for everybody. And then you have other technologies that are based on the sensors that the vehicle can equip. So you can have localization based on visions or on cameras, or you can have localization based on LiDAR. These two technologies are usually more accurate, but also you need some kind of HD maps to be able to work with these technologies. Difference between both. Cameras has issues with light, so it's difficult to work in night conditions or in foggy conditions, for example. And LiDAR doesn't have these problems, but are more expensive. So the difference between the cost of a camera and a LiDAR is some order of magnitude. So if you want to have an intelligent vehicle, which sensor, which technology you need to pick? Probably all of them, or some of them, and then fuse this information. depending how expensive you want your car to be. Then we have maps. We have the car localized, so we know where we are. Now we need to move. So let's say for the decision making, we have 3 stages. So we have global planning, behavioral planning, and local planning. So global planning is where we want to go. Behavioral planning is what we want to do next. And local planning is how we go there. So let's start with the global planning. So we need SD maps for that, of course, and we need big SD maps because in cars we usually need to drive several kilometers. And the most common technologies are graph-based. So these technologies come from computation technologies, are really old. So I think these tries from the 70s, but are still on use. So this is what Google uses in your mobile phones, for example. Real-time capabilities are less relevant. So you want to search for a ubication, and then you don't care if you need to wait 2, 3, 5 seconds. This is less relevant. And the classical algorithms only use geometrical information, so how to get from one point to the other. Modern algorithms use more data, so enriched data. For example, white type restriction, you can select in your mobile phone, okay, I don't want to go to rural roads, for example, and then replan according to that. It uses speed limits to calculate what is the faster route, or even use things like traffic flow situation in a way that you can avoid slower routes depending on the time, depending on the situation. And the future step is doing cooperative planning using V2X technology. So now we have some information based on data received from the mobile phones, but if we can communicate between the vehicles, we can enrich this information and make the global planning even better. Then we go to the behavioral planning, and this is what we need to do next. So we need to modify the car behavior at any point, depending on the situation. So for example, we're approaching to an intersection. We need the car to slow down before the intersection. We are following a car that is slower than us. We need to think, okay, can we overtake or not? So this is what a human is doing, but we need the car also to understand and do that. And you can do that in several ways. So for example, you can modify the planner constraints. So you have a planner, an equation, you have some constraint, what is the maximum speed. You can modify that depending on the current behavior that you want to follow. Or even you can change the planner. So you have a local planner that is really good for high-speed driving, but that usually is not really good at parking. So if you need to change your behavior, because now you need to park, you can even change all the planner itself. And let's say the classic way, so behavioral planning is something that was not there at the beginning when they begin to think, okay, let's think about intelligent vehicles. And they try to solve everything with the local planner. That is possible, but it's really hard to do. And especially, it's really, really, really hard to debug. So when something bad happens, if you have this kind of implementation, you don't know why. So they think, okay, let's do something that we can track and go to the state machine. So this is the classic approach, okay? So state machines are able to deal with several situations. You have one situation, you have one transition to another situation. It's easy to track, it's easy to debug, so they are a good approach. What is the problem? When the number of events begin to increase, this is really difficult to implement. So if you have 4 behaviors, that's okay. If you have 16 behaviors, that's more difficult, and you can increase and increase and increase. So this is still on use, but let's say the present and the future is going the way of event arbitration. So event arbitration is a mix between state machines. So you have an S structure with several state machines, and on each branch, you can have different selection behavior. So for example, this is an example. We have here these 3 levels, okay? And in the last level is automated driving. So you want the car to drive autonomously in this example. Then you have another level that you can divide between urban driving, between safe stop, and between parking near goal. This is priority. No, this is, cost. So if everything is okay, you drive. If you are in the end, you park. And safe stop needs to be always accessible. If you want to implement that from a classical state machine, that's really complex. You have a lot of transitions. And then inside urban driving, you have another cost arbitration to change the lane to the left, to the right, or continue in your own lane. So this is just an example. You can extend that as much as you want. And important things, each maneuver can be canceled. So you need to be able to cancel a maneuver if you cannot commit anymore. Just think about an overtaking. At some point, you can think, okay, overtaking the other car is a good idea, but then you see a car that was not visible before. You need to cancel this maneuver. And also that safe maneuver is always feasible. You need to keep the car always in a situation where you can stop the car without crashing. And if you like this idea, also the KIT MRT team is developing an open source solution based on several thesis dissertations. That's behavior planning. Now we go to the local planning. And this is basically the question. So we want to go from here to there. What's the best way to do it? Then there is a lot of techniques to do that. So we have techniques based on graphs like Dijkstra, like lattices, A*. We have techniques based on different geometric approach, so clotoids, polynomial, Bezier curves, splines, or we have techniques based on functional optimization, for example. All of them are valid. Some of them are better for some kind of planners than the other. For example, for parking planners, lattices and A* are really good. For high speed planner, so for high speedway, not so good. But it will depend what is your computer, what are your inputs, what are your sensors to select one or the other. And then just to conclude about this decision, just an example that is overtaking. So in overtaking, we have the behavior, we have the local planner at the same time. So first, the behavior, we are following another vehicle, and we perceive that the vehicle is slower than ours. We know from the map that lane change is possible, and then we plan accordingly. Okay, we want to go there. Then here we have, this is the planning trajectory. This is planned by one of the algorithms selected. But we also need a speed planner to plan what is our speed. So not only the position, but also the speed of the vehicle. Because in the end, the actuators that Francisco will talk about that later need to press that on a speed pedal. Then we reach this position. We have another state of the behavior that is passing the other vehicle. So we cannot keep in this lane forever. We need to know how much we keep in this lane according to the current situation. And if the situation changes, we need to replan. So if this car begins to accelerate because don't want to be overtaken, we need to decide again. We continue overtaking, we accelerate more. So this is something that is continuously replanning. And finally, we need to finish the maneuver that, of course, we can select different behaviors. We can cut the car in a more aggressive way. We can be more conservative. That will depend also on the other obstacles that you have in the environment. And this is just a brief summary of what is the decision from an intelligent car. And I will let now my colleague Francisco to continue.
Thank you very much, Eduardo. So now we're going to move to the third presentation of the day. This is going to be conducted by Dr. Francisco Martín Navas. He he got his PhD from École de Mines, no? In Paris, and he's been working for Renault for a few more years. He's been since 2 years, okay. Yes. And yeah, so he's going to talk to us about controller supervision. So, Frank, whatever you want, you have the stage.
Thank you, Fernando, for the presentation. So I will take it back where Eduardo left it. So he said he just generated a path and a specific speed profile that the vehicle should be able to follow somehow, and that's what control is for. So this model, control, is receiving the information with that trajectory and the speed profile, and the whole point is to be able to calculate the control variables. There is some kind of classification into control. The first one is the one divided into high-level and low-level controllers. High-level are the ones dealing with the navigation commands minimization, and low-level controllers are the ones really touching the actuators in the vehicle. There is also a second classification, which is related to which vehicle dynamics you're touching in the vehicle. You have the longitudinal one, really actuating through the throttle and the brake, so longitudinal direction of the vehicle. And then we have what we call the lateral control, which is the one dealing with the steering angle of the vehicle, and thus making the vehicle move laterally. So if we dive into the longitudinal control, here we can see a typical feedback control architecture. We have a vehicle there with a sensor that is able to measure the speed. And this speed is compared to the reference velocity that we receive from the navigation. So we can have an error which is going to be minimized by the high-level controller by calculating a desired acceleration. This desired acceleration is going to be taken by the low-level controller, and that is going to be the one that is going to tell us how much brake and throttle we should input in our car. Just mention that control, it will be fully dependent on what kind of vehicle you're using. It's not going to be the same to control this golf car here. If you try to push the throttle here, will be different than if you do it in the Renault Alpine. The dynamics will be totally different. Now let's first focus into the low-level controller. I'm gonna tell you how this is generally done in the literature. So as we said, this is the one taking the output of the high-level controller, which is the desired acceleration. And we need to have a way to translate this desired acceleration into a specific torque by having some vehicle drivetrain dynamics, and also by knowing the different forces that you could apply into a vehicle, like aerodynamics, forces that you have for friction with the road and the tires, also inclined roads, etc. So once you have this torque, either for the throttle or the brake, what we usually do is we have to do some kind of experimental map translating the torque that we desire into a specific brake or throttle position. So the output of this will be, okay, we have a way to translate our desired acceleration into a specific brake and torque angle. Once this is done, this low-level longitudinal controller is used together with a high-level controller, so we could follow the speed profile that Eduardo was sending us through the navigation. The thing is, nowadays in the literature, we don't use high-level controller just before low-level controller, but we use the low-level controller in a let's say feed-forward control version of the thing. This is done this way because in that way we can have the low-level controller used as a predictive component, having the high-level controller acting only for correcting minor errors related to either disturbances, external disturbances that you could have in the car, or even some model inaccuracies, because we all know that even if we try to model the wall as perfect as possible, it's never going to be perfect enough. This kind of a structure is given better tracking capabilities, and that means that we are able to follow even faster the reference speed, which is really important. Could be really important, for instance, in some kind of emergency braking decision. We want to stop the vehicle as soon as possible, because otherwise the decision could have been taken too late. And just to mention that this kind of high-level controller, usually in the literature, is enough with a PID controller, at least for electric vehicles. Now, let's move on to the lateral controller. Again, we have a typical feedback control architecture. In that case, we have the vehicle position given by the GPS, by a sensor. And this one is compared to the reference path coming from the navigation. So we could calculate the input of the high-level controller, which is going to try to generate a desired steering angle that is going to be the input to the low-level controller. The lateral controller aims to follow the path as close as possible. And by that, the goal of this kind of controller is going to be to follow that by minimizing some kind of specific errors that I'm going to explain to you in this slide. For lateral control, usually we define like two different kind of errors. We have the heading error, which is what is the angle difference between the vehicle's orientation and the orientation of the path. And then the second one is the cross-track error or lateral error, which is simply the gap, the distant gap between, in this case, the front wheels, and the perpendicular to the path. The reference here could change. I mean, you can find anything in the literature, but either it's rear, middle, or front axle. Once we have these errors, as I said, like one of the most important steps in control is to be able to have a good model. Without a good model, we're not able to do a good controller. That's the truth. So we need to also obtain some lateral vehicle dynamics and a lateral model where it's going to try to translate is how a specific steering angle will affect the lateral movement of the car, taking into account like forces between the road and the tires. In the literature, we can find like mainly three models. There is the bicycle model, which is a simplification of a vehicle model that is putting all together into two wheels joined by a rigid axle. We have the kinematic bicycle model, which is the more simple one, and is usually suitable for low speed and low slip conditions. And then we have the most used in the literature because it's more complete, which is the dynamic bicycle model. And this one can go from low speed to high speed and also include low slip and large slip road conditions. Finally, I also like to mention that you also have more complex models, like four-wheel vehicle dynamic models, and those you use them for more complicated control problems like drifting control or controlling really at the point of stability of the car. So once we have a model that, as I said, we need to have this model as close as possible to reality, we need to choose a lateral controller. And in this case, it's not like in the longitudinal controller that I showed to you before. Here we have many options, much more options. You can tell it's a more like kind of hot topic in research. We have like a main classification, which is geometric controllers, which is using the basic trigonometrics from the path together with a vehicle, and it's also using the lowest speed kinematic model. And in here we can find pure pursuit and Stanley controllers. But as we said, that this one is using kinematic models. One of the disadvantages of this kind of controller is that it's not possible to use it for high speed, medium or high speed. But it's really good to do some stability analysis and all that. It's kind of easy to use. On the opposite, we have like some kind of full range application controllers, which are like dynamic controllers. And here we can find, I just mentioned a few, there is way more. TNC control, model predictive control, and also like optimal and rules controller, linear parameter varying, age infinite, and so on. The most popular right now in the literature is, of course, model predicted control. Because, I mean, just with a model, it allows you to have like a wide range of different constraints that you can apply to the controller of your vehicle. But the problem with that one is usually that it's kind of difficult to analyze the stability of the controller. And also you need a kind of powerful computer to be able to run it. So it will be a bit more difficult to put it in a vehicle ECU, for instance. Finally, I wanted to put some videos and just quickly mention some work that is going on right now in the control side. As I said, modeling can be kind of complicated sometimes. We have a lot of non-linearities. We don't have all the data because the constructor, they don't give away the data maybe. Or maybe we need to perform some complex tests in order to have the value of some parameters. So at the end of the day, we have a simplified model. And maybe with that simplified model, we can have like the best controller possible. So something that is like a hot topic right now is, okay, let's try to use deep learning to improve our model online. And once we have a better model, we're gonna like synchronize the controller so the behavior is gonna be improving with time as long as we're gathering data. I just wanna quickly click in this video. I'm not sure if it's working. Do we have internet here? Yes. No? Okay, but if you put this in YouTube, you can find the video. It's really fun to see. I mean, basically it's like a racing car. You have like 12 laps. And you can see like with every lap, the controller is doing better because you're able to finish the lap in less time. And then I have another video here that it was talking about controlling cars on the point of stability, and basically you have a car drifting all the time. Yeah, finally, I wanted to mention how important it is also in intelligent vehicles to talk about human-machine interface. Because human-machine interface is the way that the vehicle and the technology has to communicate with the passenger or the driver. It's allowing also the user to change how the driving feels inside the car, like lane change, desire speed, emergency stop, and others. But something really important right now, and when we saw the introduction done by Carlos with a different level of automation, is HMI is going to be really important in how to communicate with the driver, with the passenger, with the driver in the case of level 1, level 2, and level 3 automation, how to communicate with them when they should take control of the car because the technology doesn't know how to handle the situation. Finally, some conclusions. So through this slide, we have seen an intelligent vehicle architecture that I think is kind of paving the way to have fully autonomous vehicles. Because this same architecture is the one is used right now for having advanced driver assistance system, ADAS, level 2, level 2 plus, and level 3. What I will say that is kind of missing to reach this kind of level 5 fully autonomous car, well, of course we need some improvement on legislation. We also need, there is also still work to do regarding technological bricks, and also try to do like things that are more performance with less sensors, or like solutions that are kind of cheaper. But I mean, a conclusion that we have say, we already have nowadays intelligent vehicles on the streets, and we can all buy them. Well, thank you. Questions, or I don't know how we proceed.
Yeah, of course, we have a small round of questions. So if there's anybody here who wants to make any question.
Yeah.
Okay, I'm bringing the microphone.
Is it for me or for some of my colleagues? Oh, for me, okay.
I'm not sure if it's working.
So I have a question regarding the modal predictive control, because you have stated that it's the most common in the literature. However, there are some points that I don't know if you are working with that and how you address that, because in fact, modal predictive control, there are some things that you cannot address properly, maybe like H infinity, such as the uncertainties or even the delays in the communication or whatever. But also some problems that we are struggling with is like, you need the full state knowledge when you work with modal predictive control. And for example, there are some states that might be difficult to obtain, such as, of course, side slip angle or even roll angle. Mm-hmm. Well, high-cost sensors, you can obtain those, but how do you deal that in practical applications?
I mean, as I said, I work for Renault, so we have to put things in easy use, and that's kind of complicated. I mean, I don't specifically use model predicted control because it wouldn't fit into a vehicle ECU nowadays. I just wanted to mention that, I mean, it's a hot topic, and it's really fashion to work in model predicted control. But of course, it has, as you said, it has some drawbacks that it's difficult to analyze stability, robustness to uncertainties, and all that.
Thank you very much. While we wait for more questions, I have one for Eduardo. This is a very controversial question. You can use that microphone that you have over there. Autonomous car with map or without maps?
I will say,
Do you turn it on?
I will say both. So we need maps for global navigation, at least. We need SD maps to be able to drive more or less safely, but we also need to be able to drive mapless, because the maps cannot be always up to date. This is too expensive. We cannot guarantee that. We cannot guarantee that we are able to redo, let's say, construction area. So we need to be able to also drive mapless. That will be my answer, and I think if we are not able to do both, we cannot go to level 5 cars.
That's very interesting. So, but at the end, you do recommend to use also maps, no? So it's because there's both ways. That's those trends. So I guess it's important, no?
Yeah, but I think that you can do in parallel things, but you need to convert. In this presentation, fusion was like a hot topic. Yeah. So we also need to fuse mapless and map-based driving.
Thank you very much, Eduardo.
Is it working? Yeah. So I would continue with this interesting exchange regarding maps, because I think, of course, it's a very challenging question. So in your opinion, is it feasible to deploy autonomous vehicles in cities without maps?
So 100% without maps? No. That's my opinion. So not
When
the
I
Renault
say-
opinion.
When I say, no, that's, I mean, I think it's a very complicated question to answer. There's no only one answer. But I would be more precise on that. I'm not referring to maps in general, I'm referring to HD maps. So, is it still the same answer? Do you think it is not possible to deploy autonomous vehicles?
Without SD maps?
Yes.
Yes, I think that with SD maps should be enough for driving in most of the situations. But it depends if you want to go to really level 5 vehicles or you want to keep on level 4, level 3. As much as you want, so if you want level 5, you need better data. So probably you need HD maps or pseudo HD maps for that.
Okay, thank you.
Thank you very much for the question. More questions?
Thank you for the presentation. Is I'm audible? Is I'm audible? Yeah. Thank you for the presentation. I want to ask one question. There was one line written in the presentation, cooperative planning using V2X technology. So what is this one and what is the future scope related to intelligent autonomous driving with relation with the cooperative planning using V2X technology?
Yes, so I was referring about that in the presentation for the global planning, and this is also a hot topic at the moment. So we didn't include that to not make the presentation really long, so we didn't talk about V2X technologies, but this is something that also helps you to enable more information. So I talk about global planning, but that also includes V2X for improving perception. So in the end, the more data, the better data that we have, the better results that we can. So I think that for global planning is really useful. For local planning can be useful if we make cooperative driving, but then we need that all the vehicles are intelligent.
Okay, so global planning here refers to like what your factors you are accommodating in the global planning.
Oh, for example, we can improve the traffic jam detection, because at the moment we detect traffic jam using mobile phones of people, and you say, okay, if this mobile phone is slow in this area, for sure there is a traffic jam. If you have a road unit that is really seeing this intersection, you can be sure if there is a traffic jam or not. So then your data is more accurate. Maybe the result for a normal user is not too much different, but you will improve some situations.
Okay, thank you.
Thank you very much. More questions? I have one for Carlos. Carlos, you were mentioning about them that I didn't get very well. That you were mentioning that the future is something like not using GPUs. Could you elaborate that a little bit more? Because for me it was a little bit confusing and scary because I use GPUs in projects. So.
Yeah, of course. No, in the near future, GPUs are here to stay. But the thing is, GPUs are ready mainly for images. When you have these LiDAR or radar clouds, then the data is sparse and it's not so good for that. Because, for example, you have this sparse convolution that have to take into account that, well, the points are not together. That's the point. So the architecture of GPUs is ready for images where information is dense. For radar and LiDAR is not so good. But yeah, but at the moment, I think we don't have a real alternative for that. It's something that maybe in the future can be developed further.
Okay, interesting. Let's see. We'll talk about that in a couple of years. Let's see what the
Okay.
GPUs are. Okay. Any more questions? So I think we can close it here. I don't know if you have any more remarks or everything was said already. Yeah. okay, we couldn't have internet, so we are going to try to have in the comment section somewhere the links of the videos that Frank had ready, because they are very interesting. I have seen them, and they're a very good one. I think they really help to identify the limits of the control right now, which is very interesting. So I recommend you to go and check them once we have them available. And that's all from our side. Thank you everybody who attended this presentation. Thank you for the people in the internet watching this presentation. We're going to put an end to this. We're going to continue here, and we have a small invitation in the cafeteria that's in honor to the speakers. So we're going to have at least half an hour for that. So thank you very much, and everybody who attended is invited to come to the cafeteria for this snack. Okay? Thank you again, guys, for the presentation.